shaking up some ideas that have been around for centuries.
Exactly. We're going to unpack Izwidi's theorem. It's a totally new way to tackle high-degree polynomials.
And we've got some research here suggesting we can now find exact symbolic answers for equations people thought were, well, impossible to solve precisely.
Our mission is really to understand how this works and what it means.
What's so striking is that it's not just a minor tweak. It feels like it's reopening a door that, mathematically speaking, was slammed shut over 200 years ago.
Right, specifically about polynomial equations, finding their roots exactly.
Hmm.
So for something like 2 centuries, mathematicians basically accepted the Abel-Ruffini theorem.
That's right, Niels Henrik Abel, back in 1824.
And it essentially said, look, there's no general formula using basic operations,
Yeah.
square roots, cube roots, that sort of thing, radicals for polynomials degree 5 or higher. Sounded pretty final, didn't it?
Absolutely. For 200 years, it wasn't just seen as difficult. It was considered like proven impossible, an intellectual dead end for exact solutions.
So people moved on.
Yeah, mathematicians focused elsewhere. Numerical approximations, iterative methods, perturbation theory, ways to get close.
But never exact?
Exactly. Those methods always have drawbacks. Instability, maybe rounding errors creep in. And crucially, you don't get that perfect, precise algebraic form, just a number that's very, very close.
Okay, so if that door was firmly closed by Abel-Ruffini, how does Izwidi's work suddenly wedge it open again? It sounds like it must contradict that older theorem.
That's the really clever part. It doesn't actually contradict Abel-Ruffini directly because it steps outside the constraints Abel was working within.
Okay.
Murad Sultan Izwidi introduced this new theorem in 2023. And the key isn't just a new formula, it's a whole different way of representing and working with the polynomial structure.
So not using radicals.
Precisely. Instead of trying to force the roots into that radical format, Izwidi's method bypasses that limitation entirely. It uses different tools, things like recursive power sums, complex exponentials, and these deep recurrence patterns.
Can you maybe unpack that a bit? Recursive power sums, recurrence structures. What does that mean in practice?
Sure. Think of recursive power sums, like building something where each new piece depends on the ones you just calculated, following a strict repeating pattern. It's sort of self-referential.
Okay, like a chain reaction.
Kind of, yeah.
Yeah.
And recurrent structures just refers to those predictable repeating patterns that show up because of that recursion. It's almost as if the equation starts simplifying itself through these steps rather than us trying to wrestle it into a radical form.
And this reveals solutions using exponentials.
Yes, often complex exponentials, things that just weren't reachable within the old radical-based framework.
Wow, okay. That really does sound like a fundamental change in approach. So this new framework can genuinely give us exact, symbolic, closed-form solutions for polynomial equations of any degree.
That's the claim, and the evidence presented is compelling. It's a paradigm shift, not just an incremental improvement.
And they prove it how?
The research presents a complete symbolic solution for a really nasty 19th degree polynomial.
19th degree. Wow.
Yeah. And the solution is algebraically perfect. No approximations, no rounding. It stands as direct proof that Abel's impossibility result, which was specifically about radical solutions, just doesn't apply here because Izwidi isn't limited to radicals.
So let's just sort of contrast that clearly. Old way hits a wall at degree 5 for exact radical solutions, relies on approximations after that.
Right. Or radicals only up to degree 4.
New way, Izwidi's theorem tackles any degree, like this 19th degree example, and provides exact symbolic expression.
Often involving those complex exponentials, yes.
And error handling. Traditional numerical methods have issues with stability, rounding errors.
Whereas Izwidi's method claims zero error, pure symbolic precision.
That's a pretty powerful statement.
It is. The equation solved isn't just a math problem. It's almost like a declaration that, hey, maybe we didn't know everything about this supposedly solved area.
Okay, let's dive into that specific polynomial then. A 19th degree one. You said it's complex.
Oh, yeah. It's got a long list of terms, big coefficients. Just looking at x to the power of 19 makes you want to reach for a calculator, right?
Definitely. And hope for the best with approximations. So how does the theorem actually handle something like that?
Well, like you said, traditional methods would be prone to errors. Things like Newton's method give you approximations, but they always carry that risk of being slightly off, Rounding errors accumulate. It makes you ask, if you need absolute certainty, perfect precision, how do you get it?
And Izwidi's theorem offers an answer by breaking down the polynomial symbolically. You mentioned a recursive process.
That's right. It uses this recursive process to find the exact values of the roots, avoiding those approximation issues entirely.
So how does that recursion work step by step?
The core is a specific recursive formula. It lets us calculate these values we can call is coefficients.
Yes, isn't. Okay.
Think of them as maybe intermediate building blocks. The formula is like climbing a ladder. Each step, each less coefficient, depends on the ones calculated before it.
And as you climb this ladder,
As it computes these ses coefficients, the method essentially takes that huge 19th degree polynomial and transforms it, step by step, recursively, into something much, much simpler.
so applying this ladder, this calculation of sus coefficients, to that specific 19th degree polynomial in the research, what happened? Was there anything surprising?
Well, what was quite remarkable, really elegant actually, was that for this particular polynomial, a whole bunch of these ses coefficients turned out to be zero.
Zero. How many?
A lot of them. Specifically, 0 through S7 were 0, then S9 through S16 was 0, and S18 was also 0. The calculations themselves are complex, big numbers, but the result was this massive simplification.
Now, is that always the case or just for this example?
That's a good question. It's not necessarily a general property for all polynomials solved this way, but it was a key outcome for this specific 19th degree test case.
That's incredible. So with all the sus coefficients vanishing, the original massive polynomial just collapses.
It dramatically simplifies, yes. It boils down to just a few remaining terms.
What does that simplified form tell you?
Well, straight away, this simplification shows that one root must be x equals 0. That becomes obvious.
Okay.
But it also leaves us with a much more manageable equation. If you think of x to the power of 9 by 9 as just a single variable for a moment, what's left is effectively a quadratic equation in terms of by 9.
A quadratic from a 19th degree. That's some simplification.
It is. And then when you substitute the exact symbolic values for the few s coefficients that weren't 0 into that simplified quadratic form,
What happens then?
it gets even simpler. And here's the really neat part. The discriminant of that quadratic in by 9 turns out to be exactly 0.
The discriminant is 0, which means
It means we have double roots or repeated roots for by 9. So by 9 itself simplifies down to just a single exact symbolic value.
amazing.
And from there, the research shows how you derive all the exact symbolic roots for the original 19th degree polynomial. They end up being elegantly expressed using complex exponentials.
And crucially, no approximations were needed at any point.
None whatsoever. That's the power here. The roots derived are exact, purely symbolic. They aren't subject to the small, potentially compounding errors you get with numerical methods.
So this ensures we can find these roots perfectly, even for these incredibly complex high-degree polynomials that classical methods just couldn't handle with this kind of precision.
Exactly. It demonstrates a capacity that was previously thought impossible.
So stepping back, what does this mean for mathematics more broadly? It really feels like the problem of solving high-degree polynomials exactly isn't impossible anymore.
It suggests it's not, at least not in the way we thought. That door Abel closed on general radical solutions seems to have been bypassed. We've entered a new space, a different way of finding solutions using these structured recursions and exponential forms.
It really pushes the boundaries of algebra, doesn't it?
Significantly, it shows that even in fields we might think are completely mapped out, mature fields, new viewpoints, richer symbolic systems can lead to breakthroughs, things that change our understanding of what's fundamentally possible.
And the ability to get exact symbolic roots for any polynomial degree could have ripple effects.
Potentially huge ones, both in theoretical math exploring new concepts, but also think about practical applications where absolute provable precision is critical.
Which leads us to a final thought for you, the listener. Consider this. Now that we might have a way to solve any polynomial exactly symbolically, how might that change fields that currently lean heavily on numerical approximations?
Think about engineering, maybe cryptography, certain areas of physics like quantum mechanics, anywhere that relies on polynomial equations.
Where else might the need for absolute mathematically guaranteed precision open up completely new avenues or possibilities? Something to think about.